Okay, today our topic is frequency response, and it is the last one for the control theory 1. So the content of this lecture are shown here. Actually, this frequency response is another type for another type of analysis on stability of a system, specifically of a closed loop system. Okay, so far you have learned root locus method to design controller specifically to find the gain k, the optimal gain k based on the evolution of poles of the closed loop system. So root locus has advantages and disadvantages. The first point, it is a good indicator of transient response. So you can see the location of the poles. If you have large complex number, then the response induce large oscillation. Okay, so it is very obvious that it's a good indicator for the transient response. And also it explicitly shows location of all closed loop poles. Yes, it's very obvious. And trade-offs in design are fairly clear. So you can see the trade-off when you see the root locus to a certain zone, certain region. It means for some system, no matter how you can find the optimal value k, you might not get the desired response. So you can see the trade-offs very clear. For the disadvantages of root locus, first it requires a transfer function model, and you need to know the poles and zeros of the open loop transfer function. And it's difficult to infer all performance metrics. You may only observe you can only make conclusion that the transient response may oscillate or not, but you cannot really have the actual metrics of the performance. For example, the percentage of overshoot, the rise time or settling times, you cannot specify it exactly. And it is hard to determine response to the steady state for the sinusoidal input. So this means you know the system is stable or unstable, but you don't really you cannot conclude on the behavior of the response that usually is very rich if you have sinusoidal input. Okay, and the last point of the disadvantage, root locus is hard to infer stability margins. Although you know it's stable, but you cannot quantify the margin of the stability. Okay, and now today you are going to learn frequency response method, which is a good complement to the root locus techniques. The first point, it can infer performance and stability from the same plot. Second, it can use measure data rather than a transfer function model. This means you have a physical system. Let's say you have no way to make mathematical modeling, but you just inject the input of the sinusoidal waveform, and then you measure the output, and from the raw data you can actually construct some graph or compute something based on some method that you are going to learn. Then you can evaluate the stability of the system, and you can even uh, find the metric of the performance matrix. The third, the design process can be independent of the system order. So you can design a controller just based on the property that you learn from the raw data, rather than uh, the modeling that show the order of the system. And the controller design does not need to care about the order of the system. And also, the time delay can be handled by frequency response method correctly. Graphical techniques, both analysis and synthesis, are quite simple. So given a system with a transfer function GOS, so GOS is open loop transfer function. And so we call G of omega here. G of omega is the frequency response function. So omega means the angular velocity of the signal that you input to the system. Okay, and it is positive. So from here you can see that the frequency response function is complex number. Okay, so for any complex number you can express it in terms of the norm or the magnitude of the complex number and the phase. Okay, so this means, so maybe you are more familiar with this exponential of phase g of omega j omega. So the frequency response function can be used to find steady state response of a system that you have input as a sinusoidal waveform here, and the output can be also sinusoidal. So the steady state, actually the steady state of the output is sinusoidal as well. Okay, so for example, if you have input E of t, the sine waves like this, and you have a transfer function, so in this case we call frequency response function, okay, that the magnitude is 0.3 and the phase is minus 80 degree, then the response, actually this is a steady state, or you can term it as a particular solution of a differential equation. So the magnitude of the input is modified by the magnitude of the frequency response function, and the phase of the output is shifted by the phase of the frequency response function. And there are many ways to display this. First, the Nyquist method, Nyquist plot. It is a graph that shows the real axis versus imaginary axis of the complex number. Okay, so we just plot in the complex plane, and it's called Nyquist plot. And actually this plot is a little bit hard to visualize and not really useful for synthesis on the stability. Yeah, it's not easy for synthesis, but it can give the definition of can define the stability test easily. Another type of plot is Nichols plot. which is amplitude versus phase. So amplitude is vertical axis. Um, yeah, amplitude is vertical axis, and the phase is horizontal axis. And the last one, bold plot. Bold plot. It is a plot between uh, amplitude versus frequency in the log scale, and also the phase versus log frequency. So for both plot, you have two plot. The horizontal axis is frequency in the log scale, so log scale, and you have magnitude as vertical axis, and similarly for the phase, you have phase of the frequency response function as vertical axis, and you have log. Yeah, this one also log. To be precise, actually it's 20 log of this, 20 log of the magnitude, and it's called decibel. So yeah, you will see again. I think you have heard of decibel, right? But you might not know yet the term decibel, or where the term decibel come from. Okay, so here let's start to see how you can sketch using the log scale. So far you have learned that the transfer function is in the form of fractional function, where numerator, both numerator and denominator are polynomial. So when you apply the log scale to the transfer function, you can easily distribute, decompose into the sum of several factors. Okay, and for the phase, interestingly, for complex number, if you have several factors, and you can split, when you want to compute the phase, you can just split in the sum manner. Okay, very similar to the log of magnitude. So these two mathematical law or rules are the key point to sketch the plots. Okay, so let's see an example. In order to plot the graph in both plot, so first you need to sketch the log of the magnitude, okay, of the complex number, where where s is substituted by j omega. Okay, very simple. So this is complex number, and then you apply the log, and you get the split of numerator and denominator. And in order to plot this, you find asymptote. Okay, to sketch it manually, you need to find asymptote. So in order to find asymptote, you find the limit of omega. So first you mark omega, omega I. Okay, look at this one. Look at one term of the split, and in general you use omega I here. In this case, omega I is 1. In this case, omega I is 10. So it's very interesting that in order to plot the log function, you just need to find the limit of this term close to 0 and this term close to infinity. So if for this term close to 0, it means omega is much less than omega I. Okay, so that the argument of the log function close to 1. So if it's close to 1, it means log of 1 is 0, right? But so this is not actual curve, but just asymptote. It means the curve must approach to that asymptote, because just approximation, right? Approximation, it means the curve is approximate to the asymptote. And another case, you take the limit of this term close to infinity, which means omega is much larger than omega I. So then you have log all of this is just approximately to be log of omega over omega I, because this term is much greater than 1. So if you plot the log scale on the omega, it looks like this term is linearly proportional to this term, right? In the log scale. So now you got two straight line asymptote. One is 0. This one from, so you draw the asymptote from actually from very small omega, which means from 0 omega, but for the log scale value, it's close to minus infinity, right? So this is close to omega equal to 0, and here is omega I. So here is omega I. So at the omega I, you draw two asymptotes. One is 0, and another one is the slope is the coefficient of the log itself, coefficient here. So in this case, it's just 1, so slope 1. Okay. So you plot log of amplitude versus log of frequency. Okay. So in order to sketch the complete frequency response functions of the example here, you need to draw asymptote where there will be more explanation here. Well, actually not. So because there are two, I have s plus 1 here, so let me rewrite this. G of s equal to 10s plus 1 over s plus 10. So g of j omega is 10 1 plus j omega and over 10 plus j omega. It's better to write this way. 10 over 10. This one is still 1 plus j omega, and this one is 1 plus j omega over 10, like this. So log of magnitude g of j omega equal to log of 1 plus j omega over 1 actually, and minus log 1 plus omega over 10 j omega over 10. So for this one, you draw two asymptotes, right? So the asymptote of the first term is 0 up to here. Omega I for the first term is 1. Omega I equal to 1. For the second term, omega I equal to omega I equal to 10, which is 10 to the 1. So for the first term, you have asymptote here, and then you have asymptote here. Okay, so and then for the second term, you have the green asymptote. This one same, but because the coefficient here is -1, then you have a downward sloping here. Okay, so the green one for the log 1 plus j omega over 10, and the orange here is log 1 plus j omega over 1, and then you add asymptote together, the orange plus the green, from 0 to omega 1, omega I equal to 1 here. So both asymptotes are 0, so you add up still 0. Okay, and for omega greater than 10, we have two opposite sign of the slope of asymptote. This one slope 1, this one slope -1. So if you add together of the slope of these two slopes, then you get 0 slope here, right? So the asymptote, the combination of asymptote is like this. Finally, you can draw the curve of the frequency response function in log scale is the blue one. Okay, which is the blue one. All right, then let us see the phase. Similarly, phase, you need to draw asymptote for the phase. So we have the split phase as well, the split term. This one from the numerator, this one is from the denominator. And similarly, we use the we need to find asymptote. In this case, we take three limits. First, limits of omega much less than omega I. Then omega over omega I close to 0. So phase of 1, which is a real number, must be 0. And the second limit is that omega is much greater than omega I. So this term is much higher than this term, which means you have like almost pure complex number. So the angle, the angle, the phase of the complex number, that the pure imagine the pure well the phase of pure complex number must be 90 degree. Okay, and the third limit is that omega is the same as omega I. So on the horizontal axis, you scale omega I. In this case, for s plus 1, omega I is 1 here. Omega I equal to 1. For small omega, so yeah, actually, in this case, there is uh, well, we need to choose it more specific, more specifically, which means omega is less than 10 times omega I. So here is 0.1 omega I. Okay, 0.1 omega I, and here actually is 10 times omega I. 10 times omega I. Okay, so you draw the asymptote of the first limit, omega much smaller than omega I, actually even smaller than 0.1 of omega I. So this is the first asymptote, and the second asymptote, this one, 90 degree here. You draw it from 10 omega I to infinity. Okay, and then because this from 0 and this 90, if you draw it a straight line, for sure that at 45 degree, at 45 degree, you will have the value on the horizontal axis as omega I. Yeah, omega equal to omega I, but in this case omega I is 1. Okay, and similarly, now you can combine asymptote of the two terms that you have split it from this. Okay, okay, so the first term here you have one asymptote, which is the orange. Okay, and so here is 0.1 of omega I equal to 1, so 0.1 here, and here for omega I equal to 10, then zero point 0.1 of 10 is 1, right? So I would say that 0.1 times 1, but here 0. Maybe I should finish this first. So here is 10 times 10 times omega I, which is equal to 1. And for the green one, here is 0.1 times 10. Okay, time. And here is 10 times 10. Okay. And asymptote, yeah, you draw two asymptotes like this, and then just connect it as a straight line. For the green one, you can draw asymptotes like this, and asymptote like this, and then connect the two asymptotes by a straight line like this. Okay, then you add up these two asymptotes. Okay, so from here to here, you have both asymptotes are 0, then you add up like this, and and from here to here, one asymptote is still 0, but another asymptote is upward sloping like this. So you have the pink one is still upward sloping, and then from here to here, one asymptote is upward sloping, another asymptote is downward sloping. When you add them together, you get zero slope. Okay, and from here to here you have one asymptote is zero slope here and another asymptote is downward sloping. So you have the result as downward sloping like this, and from here to infinity both asymptotes have zero slope. Then the result of adding them together must be zero slope. Okay, so I hope you got the idea of sketching magnitude and phase for both plot. So obviously should mark like this, mark like this, mark like this. Is there any question? Spoon? No question. Okay. So the next point is a frequency stability test. So whenever you see the term stability, then you recall the characteristic equation of closed loop transfer function. So this closed loop transfer function is obtained from feedback control architecture. You have plan G of S, and then you have the output, and from you measure the output and feedback, yeah, using negative feedback. So here you have controller GC of S. Okay. So closed loop transfer function here is the transfer function from reference input, or you can call it desired output, to the actual output. Okay, so you got the input, output like this. So the inside of the blue one is closed loop transfer function. Then the the denominator of closed loop transfer function is used to find poles, and we call it a characteristic equation. When you set this denominator to zero, you call it characteristic equation. So intuition, all point on root locus have properties that the phase must be plus or minus 180 degree. Yeah, because we can write the characteristic equation as GC of S, G of S equal to -1. So -1 here means 1 times e to the plus minus j pi. Okay. So the magnitude of this complex number is 1, and the phase is plus minus 180 degree. This means if we this means the complex number of this term, the product of these two transfer function. Uh, so this complex number, um, so the neutral stability means if I have -1 here, and so this is imaginary, this is real. So if you substitute s by j omega and it become complex number. And if this term, these products appear at -1 here, it's called neutral stability. Ah, no, sorry. Uh, in this case, we can vary omega. Yeah, sorry, this is a mistake. Yeah, actually, neutral stability said like this. You have real, imaginary here, and all s that satisfy, yeah, all s that satisfy the crossing. I mean, yeah, because s that satisfy this equation is called poles for closed loop. So if those poles are on imaginary axis, then uh, the system is at neutral stability. Okay, and for neutral stability in both plot, we have phase as 100 or plus or minus 180 degree, and the magnitude of the closed loop transfer function is 1. Closed loop, or no, L is open loop. Yeah, L is open loop. So magnitude of open loop. We only plot the open loop, right? I think it's easier to understand if we see the graph directly. So here, um, so this is the graph of Nyquist plot. So Nyquist plot, let me remind you here. Nyquist plot is um, real versus imaginary axis in a complex plane. Okay, so you can see here you have real axis here and imaginary axis here of the frequency response function gc of s g sorry gcj omega times g of j omega. Okay, open loop, from open loop. So if this term equal to -1, right, this term equal to -1, then it's neutral stability. Okay, well, so here actually it is trying to explain about gain margin and phase margin. So now let's assume that you know that when this curve, okay, when this curve is on the left of -1, yeah, now I say it's on the left of -1, but later I will explain a different terminology. uh, if this curve locates like this, it is stable. And however, if you multiply this term by a certain gain, this curve can shift to the left like this. It can shift to the left by a certain factor such that it cross -1, right? So what is the coefficient that can shift it from here to -1 here? Now you have the magnitude from 0 to here, from 0 to here. So if you multiply, yeah, from 0 to here is called gm. Okay. So if you multiply it by 1 over gm, you will reach 1. So it means this shift to here. This point shift to this point. Right? So actually, this GM is called gain margin. It means you still have a certain of freedom to increase the gain of the controller. Okay, that's why it's called margin. And we can compute gain margin by this formulation. GM equal to minus 20 log of norm of open loop transfer function. It means this product at the omega such that the phase is 180 degree. This is what it say, omega pi. It means omega that make the complex number have the play phase at 180 degree. Okay. And the term 20 log here is for decibel. And for the phase margin, so if you look at this curve, how can you is there any other way that you can have this curve cross minus 1 other than just multiply by the gain? Yeah, actually if you rotate this curve in a certain way, then this curve will cross minus 1. So this is the angle that you need to rotate. So you rotate its the angle by factor of by gamma, then the curve will cross minus 1 here. And this gamma is called the phase margin. So we can compute the phase margin phi. So actually we just uh, set the magnitude to be 1 and then we can find the frequency omega c, and then we calculate the phase based on omega c, then it's called the phase at magnitude 1. And in order to find gamma here, you use 180 degrees plus the phi. Okay, 180 degree plus phi, then it's called phase margin. Well, you may be confusing that. No, I mean, well, so how do we know that when when this curve cross minus 1, it's called neutral stability, and when it's on the right side of minus 1, the system is stable. So I need to explain it another way. So I think you don't have the concept of this, then it's not easy to remember that. It's not easy to remember how to analyze stability using frequency response method. Um, so I review a little bit about complex number. So let's say I have z complex number here as x plus jy, and so plot I can plot z in the I can plot z for the real and imaginary. So actually this is for x, this is for y. So if I take some set such that it create a closed contour like this, and if I move along the contour on like this one is counterclockwise, no, clockwise, and if I apply analytical function f of z, okay, then it become u of hy plus j v of hy. Then I map it into the complete plane of f of z. So here is u h y, here is v h y, and then I also have another contour here. And let's say if the contour has this direction, okay, so how do we know that if we map certain z inside the contour here to this f of z plane, so where will be the set of u and v on this plane? The idea is that all the point on the right side of the arrow here, on the right side here, map to the right side here. So inside here map to outside, okay. And so here outside here, the left hand side of the arrow map to the left hand side of the arrow here, and it must be inside here, okay. So actually, because for the proper system, the denominator has higher degree of numerator, I mean for the s. But then when we substitute s by j omega, then the degree of omega on the denominator is larger than degree of numerator. So when omega increase to infinity, for sure that uh, for sure that the map, yeah, the function evaluate at omega tend to infinity is at 0, okay. Omega approach to infinity, then gc of j omega times gj omega approach to 0. So it means the direction is like this. The mapping direction is like this, okay. I think I have another graph that can explain this well. So, oh here, okay, here. Okay, here. I copy this one too. So I need to draw here. Oh, yeah, I need to draw here. So if I don't explain this term, I think it's really hard to understand. Well, actually, S equal to J omega, which means along this, okay, along this axis, J omega. Then let's take a contour here. Yeah, actually, close to this one, I draw the color. On this contour, except 0, okay. And we know that all the right hand side half plane, okay, the right half plane of S, uh, so S here is the pole of the closed loop transfer function. So all the right hand side here, yeah. Uh, in order to have the set of all right hand side, I draw another half circle here, and the direction is like this, okay, like this. Then this contour map into this contour. So we can see that all the right hand side here will map into the right hand side of this curve, okay, right hand side. So, and the orange contour is obtained from this contour, okay, and all the contour of the half circle here for all approach to infinity just map to 0 here, okay, just map to 0 here. So this implies that if um, all the right hand side set in here map to right hand side set here does not cover -1, okay, does not cover -1, then the system is stable. Why? Because all the omega, all the set on right hand side here cannot map into the uh, to the set that it satisfies characteristic equation, okay. Yeah, this is very deep idea, deep explanation. It's hard for me to express this. Okay, so let's take a break for 15 minutes. I will try to explain again in the next hour.